Up until now, we have been considering finite groups and their applications to physics in this course. It is time now to shift gears and talk about Lie groups or infinite groups. Of course, we have seen a few infinite groups in the examples when we talked about examples of groups at the very beginning. However, since then we have essentially confined ourselves to discussions which will work for finite groups only. Some of those results do carry over to infinite groups as well, especially to compact groups, but we had not really discussed infinite groups in any great detail so far. In fact, we are not even going to consider all possible infinite groups. The kind of infinite groups that we are going to look at in the rest of the course belong to a special category known as Lie groups. Now, technically speaking, the definition of a Lie group is as follows. It's an infinite group whose elements form a manifold, a differentiable manifold to be precise, and choosing local coordinates on this, the group operations become differentiable functions. Such a group is called a Lie group. So what this means really is that you can essentially parameterize group elements by a bunch of numbers. Those are the local coordinates we have been talking about. And what's also important is that when you multiply two group elements, each group element comes with its own values for parameters. The resulting product group element, of course, is going to be another element in the group, so it will have its own value for the parameters. And the new parameters definitely can be determined in terms of the old parameters of the two elements which are going into the product. That's sort of obvious because the parameters fix the group elements, and when you have two different group elements, they will multiply according to the group law and give a definite group element. So what you must have is a way to compute the new group element parameters from the parameters of the elements which are going into the product. In other words, the new parameter values must be functions of the parameters of the original group elements that were being multiplied. What we demand in the case of a Lie group is that these functions must be smooth analytical functions. They should be differentiable as many times as you want. Not only that, it should be possible for us to expand them in a Taylor series. Not only does this hold for products, it also should hold for the other important group operation, that of an inverse. In other words, the parameter values for the inverse of a group element should be differentiable functions of the parameters of the original group element. Now this may sound a bit technical, but as you will soon see, we will not really have to deal with the full glory of this difficult technical definition, at least not in this course. But while we are being technical, let me just point out that it is possible to generalize this result so that instead of talking about Lie groups, we can talk about topological groups. That is, instead of demanding that we have a differentiable manifold structure formed by the elements of the group, all we really have is a topological manifold. In other words, a manifold on which a topology can be defined, so that instead of differentiability, we can at best talk about continuity. And all we are going to demand is that the function which gives you the parameters for the product are continuous functions of the original parameters, and function which gives you the parameters of an inverse is a continuous function of the parameters of the group element. Now it so happens that this is really not much of a generalization, and there was a very famous problem in mathematics, one of the famous Hilbert problems, Hilbert's fifth problem to be precise, which essentially was ultimately answered to say that topological groups are not really much of a generalization over Lie groups. So this additional advantage that you get by demanding that these functions are smooth functions are really not going to restrict you much, because all topological groups, in a way, can be thought of as Lie groups as well. However, these technical things are not really going to be very important for us. because we are not even going to look at the full glory of Lie groups in the most abstract. In physical applications, the kind of Lie groups that we need most often, not always, but most often, is a special kind of Lie groups called matrix groups. And they are much easier for us to understand because they can be presented in much more concrete terms. So almost all the Lie groups that are of interest to us are matrix groups, as I said. These are subgroups of GL-NR, that is, invertible n by n real valued matrices, or GL-NC, invertible n by n complex valued matrices for some n. And what makes them Lie groups is that the group multiplication and inverse here are matrix multiplications and matrix inverse respectively, and these operations are of course smooth and differentiable. And what we will do in the rest of the course is we will confine ourselves mostly to matrix Lie groups. Very rarely will we talk about more abstract groups which cannot have a matrix version. There are actually some important groups which cannot be described in terms of matrix Lie groups, but we will steer clear of those complications as of now. So, as far as the rest of the course is concerned, let's not think too much about the abstract nature of Lie groups. After all, for that to be done properly, we need the full structure of differentiable manifolds and calculus on manifolds, which many of you may not have already studied. We will stick to matrix groups only, where all you really need to understand to follow this are the properties of matrix multiplication, which of course is familiar stuff to all of you. Now the matrix group that we will start with happens to be the simplest possible matrix group that we can think about. Indeed, it is so simple that it might not even look like a matrix group when you first see it. The simplest example of a Lie group, as I have been saying, is a group of rotations in a plane. So, objects which are in a plane can rotate and stay only in the plane, and in this case the elements of the group, these rotations, are parametrized by a single number, which is nothing but the angle of rotation theta. Now we can identify each element with the complex number e to the I theta, and then this essentially becomes a new group, or a group with new elements, not really a new group, which are complex numbers, and the group operation there is simply multiplication of complex numbers. Note that the correspondence is between theta and e to the I theta for a reason. Rotations by 2 pi are essentially the same as identity, and here also rotation by 0 and rotation by 2 pi would correspond to the complex number e to the power 0 and e to the I2 pi, which are both 1. So in this case, the one-to-one correspondence between a rotation and these complex numbers are guaranteed. Not only can you think of these elements now as just complex numbers, you can actually think of them as matrices, one by one matrices. And if you do that, a matrix whose element, single and only element is e to the I theta, is actually an unitary matrix, simply because its inverse, in this case just its reciprocal, is 1 over e to the I theta, hence e to the minus I theta, is also its Hermitian adjoint, because here of course there is no transposition involved, just take a complex conjugate and you are done. So these 1 by 1 matrices are actually unitary 1 by 1 matrices, and that is why the group is called U1. We will have a lot more to talk about UN soon, but this particular group is what we call U1. This is the simplest Lie group that we can think about. And this U1 has very simple properties. It's obvious that U1 is abelian, because if I multiply two elements, e to the I theta 1 times e to the I theta 2, note that we can think of this both as multiplying two complex numbers, or if you want, we can think of them as multiplying two matrices, 1 by 1 matrices, whose elements are e to the I theta 1 and e to the I theta 2 respectively. Frankly, nobody really distinguishes between a 1 by 1 matrix and the corresponding number. Anyway, the product is of course given by e to the I theta 1 plus theta 2, and that is obviously the same as e to the I theta 2 times e to the I theta 1. So it does not matter which order the elements come in, the product is always the same. If you think in terms of our original picture, that of rotations in a plane, if you rotate through an angle theta 1 and then in the same plane rotate through an angle theta 2, you end up with a total rotation through an angle theta 1 plus theta 2. On the other hand, if you did the rotations in the opposite order, that is rotation through theta 2 first and then rotation through theta 1, then you would again get the same final rotation. So rotations in a plane commute, so do the corresponding complex numbers. Now we have already proved one result earlier about the irreducible representations of a group, which is for an abelian group, all irreps are one-dimensional. So U1, though simple, is a group. It has its own representations, but the only irreducible representations it has are one-dimensional. And in this case, we begin to see one major difference between finite groups and infinite groups. In the case of a finite group, the number of irreps is actually equal to the number of classes. The result actually works here in a way, because remember, for an abelian group, each element is in its own class. So essentially, there are infinitely many classes here, and U1, despite being such a simple Lie group, actually has infinitely many irreducible representations, all of which are one-dimensional. Each irrep is characterized by an integer q, and this integer, small q, happens to be the eigenvalue of a self-adjoint operator capital Q. This latter thing is going to be very important for physical applications, especially in the place where U1 plays a huge role in physics, namely as a gauge group which describes electromagnetic interactions, and their capital Q essentially is the operator which measures electrical charge. But we are not going to talk about that right now. We are just studying the basic mathematical structure of the group at this point. This is what a given irreducible representation of the group U1 looks like. As I said, this irrep is going to be labeled by the integer q, so we are talking about dq. This maps the element e to the I theta of U1 into e to the iq theta. E to the iq theta happens to be an element of U1 again, but more importantly for us, it's actually a member, an element of GL1C. Remember, whenever we talk about the representation of a group on a vector space V, basically we are talking about a map which maps elements of the group onto elements of a subset of GL V. In this case, because we are talking of one-dimensional representation, the corresponding group here to which these resulting elements must belong is GL1C, that is, to the set of all non-zero complex numbers under multiplication. Of course, the representation doesn't really span the entire GL1C. It only gives you elements in a subgroup of GL1C, which is U1, namely pure phases. And just to check whether this really is a representation or not would be is really trivial, but still, let us go through the motions anyway. Notice that the identity element has to map onto the identity of the group, and the identity element of e to the I theta of U1 is actually 1, e to the I0, and that according to this rule maps onto e to the IQ times 0, which is of course also 1. But what is more important for us is that when I use theta to represent my rotations, or when I use e to the I theta to represent them in their U1 version, e to the I2 pi, or an angle of 2 pi, actually is the same as identity, as doing nothing. Just to check whether this works, this map really respects that, note that dq acting on e to the I2 pi will give you e to the IQ2 pi, and since q is an integer, e to the IQ2 pi will also be 1, so everything works out fine there. To check whether this really is a homomorphism is almost trivial, but let's work it out anyway. D cube acting on the product e to the I theta 1 times e to the I theta 2 is the same as d cube acting on e to the I theta 1 plus theta 2, and that gives us e to the I q theta 1 plus theta 2, and that's e to the I q theta 1 times e to the I q theta 2, which is of course dq of e to the I theta 1 times dq of e to the I theta 2. So dq is a homomorphism. So whatever we needed to prove that this is a representation is done here. Of course, being one-dimensional, it has to be an irreducible representation. There is nothing further you can reduce it onto. Okay, so now we have established that the map which sends e to the I theta to e to the I q theta is a homomorphism and hence gives us a representation which has to be irreducible, being one-dimensional. But some of you may have the feeling that there could possibly be other representations, other one-dimensional irreps, which are not of this form. So let us look at the converse question. The point is, any function f which acts on r modulo 2 pi, which essentially means theta and theta plus 2 pi are to be treated as the same element. Any function which maps this to the set of complex numbers, which is a homomorphism, must be of the form f of theta e to the I q theta for some q belonging to z. So let's try to prove this. Okay, frankly, I should have mentioned one more thing, which is this is not really true for any function. This is true for any smooth function. So f of 0 has to be 1, of course, because the homomorphism maps identities to identities. Here, remember, we are talking directly in terms of theta rather than e to the I theta. I could have used that language, but it's pretty easy to use either interchangeably. So here I am talking directly in terms of theta, but because of the cyclicity of the problem, we have to use this r modulo 2 pi. And now, f of 0 is the homomorphism mapping of the identity, has to be the identity of the resulting space, so f of 0 has to be 1. F of 2 pi also by the same token has to be 1. Now, let us calculate what f prime theta is, just on the basis of the fact that f of theta is a homomorphism. From the basic definition of a derivative, f prime theta works out to be limit as delta theta goes to 0 of f of theta plus delta theta minus f of theta by delta theta. This is of course elementary high school calculus. But note that because this thing that we have here is a homomorphism, f of theta plus delta theta has to be f of theta times f of delta theta. Note that plus actually is the group operation on the group r modulo 2 pi. And now what you have is f of theta into f of delta theta minus f of theta divided by delta theta. And so what you can easily do is you can take away f of theta common and you end up with f of theta times limit delta theta going to 0 of f of delta theta minus 1, which is also the same as f of 0 by delta theta. Note that f of theta is independent of delta theta, is just an overall number, so it can be taken out of the limiting process. But notice that the new limit that we have is nothing but derivative of the function f at 0. So f prime theta is simply f of theta times f prime 0. So the value of f prime 0, which I am going to call c, is definitely a constant independent of theta. So the equation that you really have now is a simple differential equation. df d theta is c times f, and you all know how to solve this. This immediately gives a solution that f of theta has to be f of 0 into e to the c theta, and since f of 0 is 1, this gives us e to the power c theta for some constant value c. Now if this had been a map from the real numbers to complex numbers, then this would have been enough. In fact, even as a map from real numbers to real numbers, a homomorphism from the set of real numbers under addition to the set of non-zero real numbers under multiplication would also take exactly the same form. However, because we are dealing with real numbers modulo 2 pi, we have this additional restriction. F of 2 pi has to be 1. This immediately gives me e to the 2 pi times c has to be 1. So c has to be I times an integer. And thus, our function f of theta has to be e to the I q theta for some integer q. So what we had started with was the map which takes e to the I theta to e to the I q theta for an integer q does give you an irrep. What we have proven right now is that every homomorphism of the group U1, or isomorphically the group of real numbers modulo 2 pi under addition to the set of complex numbers, has to be of this particular form, e to the I q theta for some integer value of q. No other irreps would be possible. Okay, now we have all the irreducible representations of the group U1. What can we say then about a general representation of this group? A representation would in general be reducible. It will be on some n-dimensional vector space, but we know that by choosing the basis properly, we should be able to change each representation matrix to a block diagonal form. In this case, since all the irreps are 1 by 1 or 1 dimensional, the block diagonal form will actually be diagonal. So there will be a special choice of basis in which each and every matrix for the given representation will become diagonal. So the general form would essentially be something like this. D acting on e to the I theta on a given group element e to the I theta will be e to the iq1 theta, e to the iq2 theta, e to the iq3 theta down the diagonal right up to e to the iqn theta, where q1, q2, q3 up to qn would be integers, not necessarily distinct integers. Each integer of course labels an irrep, and the same irrep can of course occur multiple times in a given representation. Now this matrix can obviously be written down in this form as an exponential of I capital Q theta, where capital Q is simply this matrix. Capital Q is the diagonal matrix whose elements are these integers q1, q2, q3 all the way up to qn. Each of the qi's are integers. Now this capital Q matrix actually has deep physical significance in the sense that they talk about charges in some sense in a physical system. But for the time being, once again, this is just a mathematical object for us. For reasons which will be clear later, it is often very useful to look at infinitesimal versions of these transformations. In particular, exactly what happens when you rotate in a plane by a very tiny angle, or in terms of the U1 group, what happens to this quantity e to the I theta and the corresponding representations when theta is very tiny. Now that's very easy to figure out in this particular example. This example being, after all, one of the simplest possible examples where we could do this. And all you need to do is take a look at what happens to d of e to the I theta when theta is very tiny. Note that when theta is very tiny, e to the I theta is very close to the number 1. In fact, to first order in theta, you could write that as 1 plus I theta. And for the same degree of approximation, d of 1 plus I theta will simply be the identity matrix plus I times capital Q theta. Let me just point out that this is what d of e to the I theta is, and if you were to replace theta by an infinitesimal angle, you can replace each one of the exponentials on the diagonal by 1 plus I times qj theta for the jth one. And that means that apart from the identity matrix, you just have an additional piece which is I theta times a diagonal matrix with q1, q2, q3 etc. down the diagonal, which is exactly what our capital Q matrix is. So Basically, what we can talk about is a derivative operator for this D, and that is something which maps the deviation in the argument, in this case the number I theta, into the deviation in the result. All this, of course, to first order. So under D prime, I theta maps to I capital Q theta. Note that while the original representation mapped into the I theta into a matrix, and even if you think of the one-dimensional irreps, e to the I theta gets mapped onto e to the power I Q theta. Now while that is a simple enough function, you should realize that what is happening is that the argument is being raised to the power Q. This is a non-linear operation in general, except for, of course, for the simple case where Q is 1. So in general, the representation maps group elements into matrices in a non-linear fashion. Whereas, as you can see, the derivative of the representation actually maps deviations from the identity to deviations in the result, but in a linear fashion. And this linearity is actually going to be very, very important in what we are going to deal with later. Note that the ND representation of U1 is a homomorphism from U1 to a subgroup of GLNC. Here D, the representation maps the identity of U1, namely the number 1, to IN, the identity of GLNC. On the other hand, D prime talks about infinitesimal deviations from the identity. Now this, of course, if you think about it, is exactly what a tangent to a curve is like. Small deviations from a point as you move along a curve essentially gives you a straightish segment, and that is what the tangent really is. In a situation with n variables, this would be what is called a tangent plane. Now, I am not really going to use much of this language, which is the natural language of differential geometry, in the rest of this lecture, simply because I am not sure whether all of you would know the language, but I cannot resist at least lapsing into this language for the time being. D prime, what it does is, it maps the tangent space at the identity of U1, which are those infinitesimal displacements from the identity in this particular case, to the tangent space of the resulting point, namely IN of GLNC. Now the tangent space of IN is actually the set of all matrices. This will become clearer when we talk about these things later in more detail, but for the time being, for those of you who know differential geometry a bit, I am sure you would appreciate this. Even if you don't, I would like you to keep this in mind, that basically what we are getting into here is that the tangent space of the identity is very, very important, and this is exactly what we call a Lie algebra. So in differential geometric language, a Lie group is a manifold of which a special point is the identity, and if you move slightly away from the identity in all possible directions, here of course you can go in only one direction, but in general if you could move in all possible directions away from the identity by tiny amounts, what you would get are the tangents to the manifold at that point, and that taken all together would essentially form a tangent plane at the identity. And this tangent plane at the identity is the home for what we call a Lie algebra. This is a differential geometric view of what a Lie algebra really is. Again, we are not going to really use this language to a great extent in the rest of this course, but this is the basic geometrical structure, and in case you want to pursue this any further, it would be very important for you to also be conversant with this language. The reason why we will not explore this particular language any further here are, one, as I've already said, many of you may not be familiar with this language, and the language of course takes quite a lot of build up to learn, and two, we will be dealing, again as we have said, only with matrix groups where we can actually dispense with this language to a large extent. Allow me, however, to go back on my word, if only for a little while. While I did say that I will not be using the differential geometric language in any big extent in this lecture, at least for U1, the differential geometric picture is so easy and so beautiful that I can't resist showing you this figure at least. This is a figure which I have taken from Peter White's lectures on quantum theory groups and representations. In fact, much of what I am going to say about Lie algebra part of this course will be based on this particular book, although I am going to pick and choose, of course. Now, here you have this nice geometrical representation of our manifold U1. Here the representation is actually literally correct because U1, the set of all points of the form e to the I theta, actually does reside on a circle on the complex plane C. Now, any arbitrary point on this e to the I theta has been marked here. We have also marked a very special point, the identity, which is sitting right here. And if you go away from the identity by a tiny amount, we are actually moving along the tangent. This is our tangent plane, which here is a purely imaginary axis. Remember, the deviation from 1 in e to the I theta is of course I theta to first order, and this purely imaginary axis essentially is what we call the tangent plane or the tangent surface at the identity of our group. Now the representation essentially maps a point on U1 to a point in UN. Now UN does not have a very nice geometrical representation that we can draw, so this thing here is only schematic. We are just sort of trying to visualize UN as a kind of object which is really not three-dimensional in general. In fact, we will calculate what its dimensionality is. But basically what it does is this gives rise to a unitary matrix. Voigt calls this pi, we have been calling it D. So the map which we call D so far is pi in this picture, and e to the I theta gets mapped onto pi e to the I theta, which is of course our matrix e to the IQ1 theta to the IQ2 theta down the diagonal e to the IQn theta, the representation matrix that we talked about. This of course is a unitary n by n matrix, and a general point e to the I theta will map onto this. Now, what we are really interested in is as we go around the group manifold here, what happens is the resulting matrix moves on UN along some closed curve. If you go all the way around and come back to where you were, the resulting matrix will also change and then come back to the original value. So that's going to give you a loop on UN. Once again, let me warn you, the picture that we have for UN here is just schematic. It's meant to be an aid to the understanding, should not be taken literally. The important point is the identity will map onto some point in UN, which I am denoting by pi 1, and when you move infinitesimally away from the identity, you move along the tangent to this curve. And so the tangent to this curve, of course, is going to be given by d prime of I theta, which is pi prime I theta in Voigt's notation, and that's this matrix IQ1 theta 0 diagonal matrix with IQ1 theta, IQ2 theta sitting on the diagonal. I would once again emphasize that because our U1 is actually parameterized by only one parameter, can move away from the identity in only one direction. So as you do that, you are going to move on a single curve, and you are going to see just a specific tangent to the resulting curve on UN. So basically what my derivative map is doing is mapping a vector in this tangent direction onto a vector which is tangent to this curve. In general, if you have more parameters, and those are the ones which are going to be of even more interest, you can move away from the identity in several possible directions, and as you move away from the identity, you are going to get curves on your target space which move away in different directions. And basically what this mapping is going to do is that it's going to map tiny pieces on the original group manifold onto tiny tangent vectors in the resulting group manifold, that is resulting vector space. And this is going to be what gives Lie group theory its immense power, as I'm sure you will begin to appreciate by the time we develop this course a bit more. As I promised, we will not really be using differential geometric language very much in this course, but still keep this idea in mind. As you move on your original group manifold, the representation matrices move in some space of matrices, and if you move slightly away from the identity, the resulting matrix is also going to move slightly away from the identity along the tangent plane to your resulting manifold. So, this picture is something which is actually worth keeping in mind, because it will make many of the issues that we will develop clearer. The next Lie group that we are going to take a look at is slightly more non-trivial than this, and it is a very important group as far as physics is concerned. This is the group of all rotations in 3 dimensions. Just like U1 was a group of rotations in a plane, and it was rather simple, abelian and all that. What we are going to talk about next is SO3, which is not as simple. This is the group of all rotations, and as you definitely know by now, rotations about different axes do not commute, so we have a non-abelian group in our hands. Now, as you all know, rotations preserve length. So, a column vector x, a 3 by 1 column vector x, which can label the 3 components of a vector, changes over under a rotation to x prime, which is given by some matrix R acting on x. But this R cannot be completely arbitrary. The rotation matrix has to have this property that x prime t x prime, which is the square of the length of the resulting vector, must be the same as xtx, the square of the length of the original vector. This is, of course, what we mean by rotations preserving length. So for every x in 3 dimensions, what you have is x prime transpose x prime, which is x transpose Rx, must be equal to xtx. Or a simple manipulation will show us that the matrix RTR minus I3 being the 3-dimensional identity matrix, must yield 0 when you sandwich it between x transpose and x for arbitrary x. Now, it would be very tempting to say that this means that RTR minus identity is 0, and hence RTR is the 3 by 3 identity. However, this alone wouldn't have said that. This alone would have said RTR minus identity must be purely antisymmetric. I'm sure most of you know the proof of this by now. If you don't, work it out. It's pretty straightforward to figure out that if there is a matrix A which gives you xtax equals 0 for all x, A must be purely antisymmetric. Now, the important thing is RTR would then be an antisymmetric matrix plus identity. But RTR is symmetric simply because if you take its transpose, you get it back. And therefore RTR must be identity, or the transpose of R must be the inverse of R. In other words, R must be an orthogonal matrix. Any matrix which stands for rotation must be orthogonal, a kind of matrix whose transpose is its inverse. However, the converse is not quite true. If you give me any 3 by 3 orthogonal matrix, that does not necessarily stand for a rotation. And the reason is the following. One important thing that you find about all orthogonal matrices is that if you take the determinant of the equation RTR equal to I, you get 1 from the determinant of I, and the determinant of RTR is simply determinant of RT times the determinant of R, And because the determinant of a transpose of a matrix is the same as its is determinant, this is equal to determinant R whole squared. So determinant R can be plus or minus 1. In other words, any linear transformation which preserves length must be represented by a matrix whose determinant is either plus 1 or minus 1. And this actually is the reason why all orthogonal matrices do not represent rotations. In fact, rotations are only represented by orthogonal matrices whose determinant is plus 1. Why plus 1 and not minus 1? The answer is actually pretty easy to figure out. If you consider any rotation, which is a rotation about an axis through some angle, you can obviously think of that rotation as being built up of many tiny rotations. You rotate by a very small amount through that original axis, then keep on repeating it over and over again until you build up to the final rotation. Now, at each stage, the matrix that represents the rotation will change, but only very slightly. And that's sort of obvious. Now, the determinant is a continuous function of the elements of the matrix. After all you do when you calculate the determinant is multiply the elements together in some order, multiply them by plus or minus 1 and add them together. Each of these is a continuous operation. So changing the matrix slightly at any given stage can only change its determinant slightly. But note that there are only two possible values of the determinant here, plus 1 and minus 1. Now, since you must start from a very tiny rotation in this process, or from no rotation at all, you must have an identity as your starting point. What this is really telling me is that I can start from the identity matrix and keep on changing the rotation amounts by very, very tiny amounts so that the rotation matrices will keep on changing very, very slowly. And since you started with plus 1 and the only other option is that the matrix has a determinant of minus 1, continuous changes in the matrix elements can never make the determinant jump from plus 1 to minus 1. So, all orthogonal transformations which are connected continuously to the identity, namely all rotations, must have this property. Determinant of R is plus 1. Now, the set of all rotations are essentially a set of 3 by 3 orthogonal matrices with determinant plus 1. The set of all orthogonal 3 by 3 matrices form a group under matrix multiplication, something which we have seen long time ago, and this is the group called O3. With this particular restriction that the determinant has to be plus 1, we get a subgroup which we call SO3. S for special. So this is a special orthogonal set of 3 by 3 matrices, and special here of course means determinant is plus 1. Now, as you all know, a given rotation can be parametrized using 3 parameters. Now, what precise set of 3 parameters to use is really not predetermined. There are many different possible choices and you can use the one which you like best. But you already are aware, I'm sure, of some of these possible representations, possible parameterizations. For example, you could use the 3 Euler angles, or you could just use the axis of rotation, a unit vector for which you need 2 parameters to specify which direction that unit vector is in, and an angle of rotation. So that's theta and n hat, again 3 parameters. Now this last one can be sort of made compact into one single entity. Instead of using 2 things, a unit vector giving the axis and an angle telling me the size of the rotation, all you can do is give me a vector which points towards the axis and whose magnitude will give me the angle of rotation. So this is a vector with a direction along n hat and length theta. So it at least seems that we can represent rotations by vectors in 3D. But what we are really looking for here is the group manifold of SO3, that is, set of all points to which I can put all these rotations in one-to-one correspondence in a nice continuous manner. Now, if you take all possible vectors, they of course form a very simple space, nothing but our familiar R3. But that is not in one-to-one correspondence with all possible rotations. That's sort of obvious because a rotation of 2 pi, for example, parameterized here by a single vector of length 2 pi, whereas the null vector would also do the same job, or a vector of length 4 pi. In fact, all vectors of length 2 pi, no matter which direction they pointed in, all those infinitely many vectors would all point to no rotation at all, the identity rotation. And there are of course plenty of such repeatations. If you take a vector of length theta and another vector of length theta plus 2 pi, they will also obviously denote the same rotation. You want to make this one-to-one? Well, you have to restrict the range of the angle. Now, while it is sort of natural to think that the range should be 2 pi, actually the range that we are looking at is the theta should be a positive number which is less than or equal to pi. The reason why we need to keep the angle restricted to pi or below is as follows. A rotation through an angle theta about an axis n hat happens to be exactly the same as a rotation through an angle 2 pi minus theta about the axis minus n hat, that is, about the opposite axis. Hence, if any rotation exceeds pi, we can always switch to the opposite axis and use a smaller angle of rotation about that axis. Since we are taking vectors in all directions, if we had allowed rotations to go all the way up to an angle of 2 pi, which seemed the natural choice, we would actually be counting each rotation twice. Once as a rotation through theta about axis n hat, again as a rotation through 2 pi minus theta about axis minus n hat. In order to prevent that, we need to keep our vectors limited to a maximum magnitude of pi. Now, if this were all that were involved here, then the group manifold for SO3, basically, which is a fancy way of saying set of all elements in SO3 corresponds to this particular thing, would simply have been a ball of radius pi. A ball of radius r is a set of all points whose distance from the origin is less than or equal to r. Technically speaking, this is a closed ball that we are talking about. So the set of all rotations can be put in an almost one-to-one correspondence with points in a ball of radius pi. There is a small catch here, as you can see in the use of almost. And the point is the following. For a point right on the surface of this ball, that is on the sphere of radius pi, for that we have n hat pi in our ball. We also have minus n hat pi in our ball, and these 2 points, n hat pi and minus n hat pi, are the same rotation. So we have managed to get this one-to-one correspondence going almost perfectly, except for the fact that it is messed up by the fact that every point on the surface of this ball talks about the same rotation as the point which is antipodally opposite to it, and yet on our ball we have 2 distinct points. So the one-to-oneness is messed up that way. Now there are some ways you can think about of getting rid of this one-to-oneness, but the cleanest way of doing this is to pretend that we have this ball for which there's nothing special going on about all the interior points. They all are just standard points in space, but on the surface itself, 2 antipodal points are to be treated as one and the same. We have already discussed in some detail the topological features that occur because of this special structure of the SO3 group manifold in one of the earlier discussion classes. Let me just remind you that this particular group manifold belongs to a class of manifolds called doubly connected manifolds. And this simply means that here the group manifold is not simply connected because there are loops which you cannot shrink down to a point continuously, namely loops which start and end at two antipodal points on the surface of the sphere. These are loops because the antipodal points are actually the same rotation, but you cannot continuously deform them to a single point. On the other hand, the doubly connected terminology comes in because if you take two such loops in succession, you can always shrink the composite loop down to a point. We had discussed this in some detail earlier, so I'm not going to go through that all over again. One very important point here is that SO3 happens to be homomorphic to another group, the group SU2, the group of special unitary 2x2 matrices, which is actually simply connected. And because of this, SU2 is called the universal covering group of SO3. The connection between SU2 and SO3 is actually very important in physics, and we are going to explore that in the coming lectures.